All right, well, thanks a lot, everybody, for coming out. There's actually handouts in a box up here. If anybody wants any, you're more than welcome to. You can grab them or pass them around. I don't know if anybody wants a copy of the presentation. You can either get it now, or if you want a copy afterwards, they're in that box. I think I forgot to announce in the earlier session that I had them here. But anyway, so I'm here to talk to you guys today about climate change in the Mid-Atlantic from various perspectives, from global to local. So I'm a hydrologist with the USDA Agricultural Research Service out of University Park, PA. And so the talk is really kind of looking at these changes in extremes, water extremes, heat extremes, things like that. And just kind of as an example, this is a picture of one of the watersheds where I work. And this is flooding, some extreme flooding that we had in 2011, and just kind of shows kind of the changes from extreme wet to extreme dry that we can experience just even in our own watershed. So here's really, really low flows that we've experienced in one of the drier stretches that we've had in the past decade or so. And so these kind of changes from extreme wet to extreme dry are kind of characteristic of climate change. So those will be some of the things I'll try to touch upon in my talk. So I've got this talk basically divided into 4 sections. Looking at anthropogenic climate change at the global and the national level. So just giving you guys a sense for recent national and global trends in climate. We'll kind of take a zoomed in look to Pennsylvania, where I do my research, the experimental watershed where I work, which is in east central Pennsylvania. It's the Matango Creek experimental watersheds near Klingerstown, PA. I'll try to give you a sense for projections, some climate projections for the entire Northeast, but including the Mid-Atlantic region. So looking out maybe early to late century, out to 2100. And then where can you find more info? So I'll provide some resources on, information on just where can you find it. Climate projections for seasonal and weekly forecasts and things that look all the way out to 2100. And so I'll try to give you a sense for some of the resources out there, as well as stuff that USDA is doing in terms of adaptation for farmers and foresters and things like that. So let's start big picture. And the big picture is this, that the warming of the planet is really unequivocal at this point. There's really no debate amongst scientists or major scientific organizations or world organizations about what's happening with the global average temperature, and that CO2 is the main driver of our temperature increase. And so this shows the carbon dioxide concentrations in the atmosphere. This is going back to 1880, so just prior or around the onset of the Industrial Revolution. So CO2 concentrations over here, this is about 280 parts per million. This is about where we were before the onset of the Industrial Revolution. And you can see the uptick in carbon dioxide concentrations as we go towards 2016. And here we are in 2016 at about 404 parts per million of carbon dioxide in the atmosphere. You can superimpose on that the global average temperature trends. These are actually anomalies, so these would be differences relative to the global mean temperature, and that's what's shown here. It's 14 degrees C would be global average temperature calculated with long-term data. That would be 57 degrees Fahrenheit if you translated that to Fahrenheit. And so all the blue is everything that was less than the global average mean, years that were cooler than normal. All the red are years that are warmer than normal. So you can see 1880s till about maybe the 1940s, 50s or so, mostly cooler than normal with a few kind of oscillations between warm and cold. And then ever since the mid-70s, all the way through 2016, nothing but warmer than normal. And in fact, a major, major increase in temperatures such that 2016 is going to be the warmest year on record. It's going to beat 2015, which was the warmest year on record last year. And so we're about 0.8 degrees Celsius warmer than the global average temperature. And so basically the planet is warming, and there's no debate about that. You can take a look further back in time if you want to see how unique this period is relative to things that have gone on over millennial timescales. So looking back hundreds of thousands of years, you can take ice core data, and that's what I've done here is just take the ice core data from Greenland to show you what carbon dioxide concentrations look like in the atmosphere and how they've changed so markedly over the past century or so. And so we really haven't seen over the past several 100,000 years, carbon dioxide concentrations exceed 300 parts per million in the atmosphere until 1950, when we crossed 300 on our way to 404 in 2016. And so these oscillations that you see here, where we have higher concentrations of CO2 and then much lower, we're kind of shifting from almost as high as 300 and maybe as low as 180. You can see these kind of ups and downs. Where we have higher concentrations of CO2, those are interglacial periods. Those are periods where it's warmer than normal. We're currently in an interglacial right now in the Holocene, so it's a warmer than normal period. Where CO2 is depressed, these are glacial periods where you've had expanses of ice covering good chunks of the planet. And so if you look at the most recent trends, this is where we are right now. And you can see we would have been heading downward. There's a distinct beginning of a downward trend. We were going to oscillate back into another one of these glacial periods. Of course, that would happen over many thousands of years. But instead, because of fossil fuel burning and CO2 emissions, this is our current trajectory. It's up. And so the planet is warming in response to the increased CO2 that we're putting in the atmosphere. And it's anomalous relative to anything that's happened over the past several 100,000 years. And so that's just to give you a sense for how unique this time period is that we find ourselves in. In fact, it's so unique, you have to go back 3 million years to the Pliocene to find a time in Earth's history when CO2 concentrations were similar. That's 3 million years ago. And so that's how unique the current carbon dioxide levels are in the atmosphere. And that's why the planet is responding the way it is. This graph gives you a sense for how warm 2016 is relative to all the years that had been monitored since the 1800s. These are global average temperatures at a monthly level, and you'll see 2016 how much it jumps off the top of the top of all the other years prior to it. It is so much different than any other year we've seen, and it will be the warmest year on record. And in fact, over the summer, it was estimated that was probably the warmest summer we've had in thousands of years. And so just give more change, just got to see. 2016 just stands out as a warm year. And so these kind of records are falling all across the globe. And you can look at monthly records, for example. There are a streak of monthly temperature records that we've been setting back to May of 2015, for example. So you can go back to May 2015. It set the all-time record as the warmest month on record since the 1800s. But in May 2016, it beat May 2015. And June 2016 beat June 2015, and all the way through September. And September actually set the all-time record, at least according to NASA. October, they're still looking at the data, but it looks like it won't set the record. So for 17 straight months, we had global monthly mean temperature records. October is a little in doubt, and actually NOAA said that September of 2016 either tied or was slightly cooler than 2015 of September. So at least 16, if not 17 months, we set global mean temperature records. You have to go back to February of 1985 to find a month that was cooler than the long-term global average. So anyone that was born after February 1985 has not experienced a cooler than normal month. So I was born in the 70s, so I had the luxury of experiencing some cooler than normal months. But anyone who's born more recently has always lived in a much warmer than normal climate. That's really the take-home message there. If you look at the US in general, most of the US has been warming since the temperature records began in the 1800s. This is showing changes in temperature relative to the 1901 to 1960 average. They're using that as kind of a baseline for our normal climate. And here, if you kind of zoom in the Northeast, you can see how temperatures have been changing. In the 60s, we had a cooler than normal decade, but everything after that, the 80s, 90s, and 2000s has been kind of on an upward trend in terms of temperatures. In fact, the only place in the United States that's been cooling at all, paradoxically, is kind of the southern, south central, southeast U.S. Everywhere else across the U.S. has been actually on a warming trend. If you just look at summer heat, this shows for the northern hemisphere how our climate is shifting. This is kind of the normal range in temperatures. This little bell curve here is kind of our normal climate. And you can see we're losing these cooler extremes, and we are shifting into warmer extremes that we've never really experienced before. 3, 4, 5 standard deviations from the mean. This is the mean. This would be our average temperature, and these are warmer than average temperatures. And these are extreme heat conditions that at times humans haven't really experienced before. And so it just shows how our climate is now shifting to warm and leaving some of the colder extremes behind. And this was done by James Hansen, who was a climate scientist with NASA before he retired. And actually, James Hansen really kind of helped to put this in perspective in a kind of an interesting way to communicate, what's happening with climate. He says, we should think of this in terms of dice, essentially. If we think of our old climate, the one from 1950 to 1980, you could consider it as kind of, basically a set of dice where, 2 sides hot, 2 sides blue for cold, and 2 sides white for normal. We now need 4 red sides to describe our current climate, which means that if you're going to roll those dice, you're going to more likely roll hot than you're going to roll cold or average. You're just more likely to see heat now than you were before. And that's just looking at it in terms, of annual average temperatures. You can also consider this in terms of record highs and record lows. There's been a lot of work just looking at, the ratio of record highs to record lows across the U.S. is looking at it at a national level. And so this just shows the ratio of record highs to record lows and how they've changed. You look at the 1950s, basically 1 record high for 1 record low, and they're kind of balanced out. 60s and 70s, actually more record lows relative to record highs, but ever since then, it's been on the uptick. Now it's 2 record highs for every 1 record low in the 2000s, and if you look at 2016, it's actually 6 to 1, just for that year. So the ratio for the US is 6 to 1, 6 record highs for 6 record lows. You can go at the city level, like Washington, D.C., it's more like 20 to 1 for 2016. So in some places, it's setting many, many more record highs relative to record lows, but at the national level, it's 2 to 1 for the most recent decade on record, and more than likely that's going to go up, as we close out, this decade. In terms of rainfall, we're seeing changes in rainfall, which are reacting to changes in temperature. Because there's more moisture in the atmosphere now. And so we're seeing greater amounts of annual rainfall, particularly in the Northeast. So rainfall totals are going up, sometimes as much as 15% in some parts of the Northeast. So this is annual rainfall amounts, how much rain we get in a given year. And those numbers are going up. For those of you, who garden or are farming and are responsive to growing seasons, you note that growing seasons are changing. They're longer by about 10 days on average than they were before. So you have longer growing seasons in the Northeast. You've got even much longer growing seasons out in the western U.S., but everywhere across the U.S., growing seasons are changing. They're getting longer. And we're getting more extreme rains. And if, folks who live anywhere on the eastern seaboard or in the Mid-Atlantic region have probably experienced rainfall extremes and probably, noting that they've probably, that they're going up. In fact, in the Northeast, we've seen the highest increase of extreme rains of anywhere in the U.S., a 71% increase of the heaviest 1% of daily rainfall events. So there's been a huge increase in extreme rainfall events in the Northeast. And I can just give you a local example. I'm from State College, PA. And just last month in October, we had, a 1,000-year rainfall event. We got 3 months of rain in 4 hours. And here's the radar estimated rainfall from those storms. These kinds of events have been happening elsewhere. They happened in West Virginia this year. They've happened in other places, and they're happening with more regularity. But here in State College, just northwest of State College, we had 7 to 9 inches of rain in a 3 to 6 hour time span. I mean, that produced catastrophic flash flooding, landslides, and if you've got, farmland, and, that's the kind of stuff that would produce massive erosion, gullying. I mean, that's an epic amount of rainfall to get in a 3 to 6 hour time frame. I was sitting at home, and I felt like someone had a power washer pointed at all sides of my house for 4 straight hours. I've never experienced rainfall that intense, but intense it was. And so you get these kind of events, and when they happen, they can be rather problematic. And so we're seeing these kind of events, and you might ask yourself, okay, so this shows here a picture of some of the flash flooding from Milesburg on October 21st. But you might say, okay, why is this happening? Why are we seeing these rainfall extremes? Well, it's pretty straightforward. There's a simple physical relationship that just describes how much water vapor there is in the atmosphere in response to temperature. It's the Clausius-Clapeyron relationship, and all you need to know is that basically the water holding capacity of the atmosphere increases by about 7% for every 1 degree Celsius rise in temperature. So we've warmed the planet by about 1 degree Celsius since prior to the Industrial Revolution. And so there's about a 7% more water in the atmosphere now than there was, then. And so there's more water available to be rained out anytime one of these storms come along and can tap into it. And so when you these extremes can happen more frequently because there's just more water available for rainfall. And it's pretty much that simple. And so folks like Kevin Trenberth, who works for National Climate Center, will say things like this, and this kind of puts it into perspective in terms of where we are in terms of climate. The climate is changing and that we have a new normal now. The environment in which these weather events are happening is not the same as what it used to be, and all storms now, without exception, are different. They're just different. They're occurring in different conditions. They may look the same as the ones we used to have, but they're simply not the same because it's warmer and wetter than what it used to be. So it's just the starting conditions for these events is just different. And so I'll give you a sense now for the watershed where I work. Some of the things that we're seeing just locally in our watersheds. This is the USDA has a long-term agro-ecosystem research network where we look at changes in climate and hydrology and the effects of changing management on water quality, things like that. And we do this at a national level. And so we started out with 10 sites that go across the country. And these are the 10 sites. We added 8 more sites. We have 18 sites now that go nationally where we have long-term data sets that go back, in some cases, 60 or 70 years. In the case of our site, we have 45 years with the long-term data that we've been collecting. We're at the Upper Chesapeake Bay site in central Pennsylvania. And so here we're working in the Mantango Creek Experimental Watershed. It's a small watershed. It's about 7.3 square kilometers. That's 3.5 square miles in area. And within it, we're collecting information on rainfall. So every 5 minutes, we're collecting data on rain, the amount of rain that we're getting at 5-minute intervals. We do the same with temperature. We started in the 1970s with temperature. With rainfall, we started in the 1960s. And then streamflow. So we're measuring the amount of water that's coming out of it. And so basically, we know how much rain comes in, how much water goes out. We can do a water balance, and we can look at changes in climate, basically changes in temperature and other things that are going on within the watershed to give us a sense for how things are changing, with climate. So what are we seeing in our watershed? We're seeing steadily rising temperatures, just like everybody else in the Northeast. So our mean temperatures are going up. Mean maximum temperatures are also going up, and as are mean minimum temperatures. Now, the interesting thing to point out is there's actually a disproportionate increase in minimums relative to the maximum. So we're actually seeing faster increases in minimum temperatures. So the rate is about 0.43 degrees C per decade relative to the maximum temperatures. So we're seeing faster rises in minimum temperatures. And the reason for that is because it's cloudier now. We're seeing increases in cloud cover over the Northeast U.S. Cloud cover has been increasing over this general time frame, and a lot of that cloud cover is present during the nighttime, and so it keeps minimums from going as low as they would if you had clear sky and radiational cooling. We're seeing this especially in the wintertime, and so the minimums are actually rising the fastest during the winter months. But in general, it leads to this annual trend in increasing minimum temperatures relative to the maximum temperatures. And these kind of trends are being seen across the northeastern U.S. It's not just our watershed where we see this. In fact, they actually see this at a national level. And it's the diurnal temperature range is when you look at the difference between the max and the mins. And so there's these changes in diurnal temperature range that are happening everywhere. And a lot of it's tied to cloud cover, changes in cloud cover, which are tied to increases in moisture in the atmosphere. We're seeing shifting seasons too. Just like in the Northeast and elsewhere across the U.S., our growing seasons are getting longer. So we're seeing in the spring, earlier freezes. The last freeze date in the spring is getting earlier, whereas the first freeze in the fall is getting later. And so when you look at those divergent trends, you can see that the growing season is, by extension, getting longer by about 10 days per decade. So our growing seasons, and these are calculated with temperature data, just so you know. We're calculating growing season length with temperature data. But when we do this with temperature data, we see a lengthening of the growing season. Shifting seasons, we see other kinds of things that happen that are just kind of anomalous to us. Some things that we see are these, for example, like summer in March is what we had in 2012. And for those of you who've been, live in the Mid-Atlantic, you probably experienced, this event where in our watershed, this is for our, where I work, in East Central Pennsylvania, we had, in mid-March of 2012, we had 2 weeks of record high temperatures, just persistent warmth. temperatures that reached 80 degrees Fahrenheit. We did this for 2 straight weeks in March. These are anomalously warm, like 3 or 4 standard deviations above the mean temperatures for this time of year. And so all the trees were leafing out, and including fruit trees. And so right after that, we had 2 days of very hard frost that caused a lot of damage to fruit trees and also killed off, a lot of sensitive plants. And so that was termed the fall spring of 2012. It was the earliest spring in the North American record. And so you can look at the fruit tree losses due to that frost and freeze event across the US. You can see it hit a lot of the areas of the upper Midwest and the Northeast exceptionally hard, including the county in which our watershed was located. These kinds of fall springs are actually increasing in frequency as the climate is warming. But when you look out towards 2100, the projections are actually that they're going to become less common. So it's like the risk for these events right now is heightened, as you kind of look out the next 10 years or so. But then as you get further out, as the climate continues to warm, which it's projected to do, these kind of events will probably happen less often. But there's definitely the risk for these events, and when they occur, they can be really problematic, as they were, in our watershed, in 2012. We see changes in hydrology too, and so we see these interestingly divergent trends in rainfall and streamflow. So we're getting more rain, it's getting wetter, so our rainfall totals are going up. We're getting more rain every year than we used to, and there's this increasing trend in rainfall. So even though more water is going in, we see streamflow going down. There's actually less water coming out. So you might say, well, why is that happening? Well, we see increasing evapotranspiration from plants. So plants are just using more water and transpiring more water. And we're doing this at the basin level. But you can calculate potential evapotranspiration with equations like the Penman-Monteith equation or Priestley-Taylor. There's these very simple equations to figure out what's the theoretical potential of evapotranspiration. And you can actually measure it with the water balance, which is what we do. We just say how much rainfall came in, how much water came out, and the difference is what was lost due to evapotranspiration. It's just a water budget approach is basically what we do. We do it on an annual basis. And when we look at the water budget, we see that the actual evapotranspiration is going up. And it's going up faster than the potential. So we're increasing the efficiency of evapotranspiration. And that's really because growing seasons are longer. And so plants have longer seasons now. They can transpire more water than what they could in the past. These kind of trends are, supported by work elsewhere throughout the Northeast. Everybody's seeing these kind of trends. There's a few places in New Hampshire, for example, where they're seeing the opposite, where evapotranspiration is actually going down. It's kind of a paradox. And so people are looking into, well, why for some of these places is ET going down when for most watersheds it's going up. But for ours, it's going up, and it really fits with the dominant trend in the Northeast and elsewhere in the U.S. For watersheds like ours. There's some interesting seasonal trends to point out. So we see changes in rainfall at the seasonal level. We're getting increases throughout the year, but then we're getting some really big increases here, like in the fall, for example. We get big increases in rainfall in October. And this has been using our 40 years worth of data. And those big increases are actually leading to increased stream flow. We're seeing big declines in stream flow in February and somewhat of a decline in July, but the big increases are occurring in October. So even though stream flow at the annual level is going down, in the fall we're getting actually increases in flow, and it seems to be tied to this rainfall increases that we get in October. And so the kind of events that lead to that kind of an increase are the things that we tend to see in the fall with these big tropical systems that make their way up. And we've seen kind of an uptick in these kinds of events over the 40-year record that we have. Here's Tropical Storm Lee, which we had in 2011, which hit actually kind of the epicenter of that event was really where our watershed is located. We had about 14.5 inches of rain from that storm in just over 2 days. And in that general time frame, when we look at the trends, we're seeing increased intensity of rain in the fall, so it kind of fits with that story. And our stream flow has gone up, and that's a picture from the flooding that we had from Tropical Storm Lee. And so kind of an interesting thing about Lee that it's just kind of worth pointing out is that the kind of flooding that we get from Lee is characteristic of these atmospheric river type events. This is what produces some of the worst flooding in the Mid-Atlantic region and elsewhere across the United States. And so I'll just give you a sense for what this looks like. Here's Lee making landfall on the Gulf Coast, and we have a hurricane here in the Atlantic. And I'll put this in motion to give you a sense for what these rivers can look like. So here's September 7th when we got all that big rain, and then we can kind of shift over, and you can see where the moisture from this event came from. Moisture was coming out of the Gulf of Mexico, and also from this interacting with this hurricane. It's these kind of atmospheric rivers, because there's more moisture in the atmosphere now, that these events can produce epic amounts of rain, and you can see where all this moisture is converging over Pennsylvania here and producing the heavy rains that we got. So there's been a lot of research in California and in Europe looking at the frequency of these rivers and how they relate to climate change. And the suggestion is because since there's more moisture in the atmosphere, that these types of events would be logically increase. There's been really no work on the East Coast yet, but one would hypothesize that if they were likely to increase elsewhere, that we may see these kind of events increase in our neck of the woods as well. And so it's just important to point out that these are the kind of storms that can bring the big, big, big rains. And if they were to increase in frequency, then there'd be issues related to these kinds of storms in the Mid-Atlantic region. Now, there's no doubt that the rainfall from Lee was extreme. It's another one of these 1,000-year type rainfall storms, that you don't see often, but when you do get them, they're pretty big. But you might then say, well, what about storms that occur, with a little bit more regularity, like the 50 or 100-year storm? How are they likely to change? And so Art Degatano, who works out of Cornell University, has done a lot of interesting work showing that, what used to be the 100-year storm, when you look at 1950 to 1979 data, is now the 60-year storm. So a storm that had a likelihood of 1 in 100 occurring in any given year now has a 1 in 60 chance occurring in any given year. And so these events, these extreme events, are becoming more frequent. Even when you look at events that are more common than, say, the 1,000-year storm, which gets everybody's attention. And so these are kind of things that are kind of interesting. No surprise that with snowfall, with warming climate, that snow on the ground is on the decline. And so when we measure snow on the ground in our watersheds, we see that there's fewer days now with snow on the ground than we used to have in the past. And because there's less snow on the ground, we see lower incidences of snowmelt runoff floods. And so this just gives you a sense for the number of floods that we've had due to rain and the number of floods we've had due to snow by decade since the 1970s. And so the orange bars are the number of floods we've had due just to rainfall. And so not an obvious trend there. There really hasn't been any major change since the 70s to the 2000s. But then you can look at the floods that are generated by snow. We had 7 such events in the 70s, 5 in the 80s, and only 1 in the 90s and 1 in the 2000s. And so the one that's pictured here is the flood of 96. So for those of you who were around in the Mid-Atlantic region in 1996, remember the big blizzard that came on January 6th or 7th or so, put down many feet of snow, and then 2 weeks later we had several inches of rain on top of a snowpack that had many inches of rain or many inches of water stored on it, and so or in it, and produced that flood. And so, but we've only had one of those kinds of events in the 90s and 2000s. So there's been a decline in these kind of events, and this dovetails with other work out of New York State and elsewhere in the Northeast, showing that there's just been fewer of these rain on snow type events, that they're already declining and they're likely to continue to decline as we go out into the future. So just to summarize, from our perspective, as we look at the data from our own watersheds, we consider what's going on at the national and global level. Climate change is definitely already here in the sense that we already see rising temperatures and growing seasons are changing. We see changes in evapotranspiration that are clearly tied to warming temperatures. We're getting these larger, more intense storms that are augmenting our stream flows, and snowmelt is changing. It's on the decline, and so it's really no doubt to us that the climate has changed, and we're seeing these kind of responses when we look at our own data sets. So then, what does it mean? What's our climate future going to look like? Is that what you might ask, and then so what pathway are we on if we stick with the business as usual pathway for climate? And so this slide is intended to just give you another kind of long-term perspective in terms of all the climatological work that's been done, and this shows the temperatures for all of agricultural history here. And you can see that, we really haven't shifted, out of like this, 1 degree C kind of band, for where we've been in terms of, our long-term temperature history. This orange band is basically temperatures that, really are unknown to humans. And then, the red band here is kind of what we would consider dangerous anthropogenic interference with the climate system. And so you can look at these long-term climate histories that have been done, by climatologists, and it's interesting to show. So here's a paper that was in Nature, for example, that shows temperatures coming out of the last ice age and coming into this green band here where agriculture first began 10,000 years ago. And then another paper by Sean Marcotte and his colleagues in Science showing where temperature has been over the last 10,000 years when we've had agriculture, really in this green band the entire time. And only here, as we get into 2016, and we're starting to increase temperatures with CO2, this shows some of the possibilities, of where we could go. This is business as usual. This is if we don't make any changes in our emissions and where things could go. This is looking out, well past 2100, but we're looking at temperature changes well beyond, would be considered safe for climate. And then this here shows a stabilization pathway. And so, this is some of the possibilities. And so climate models are trying to internalize these kinds of projections and make sense, at least for the near term, what, climate might look like. And so I'll try to give you a sense for at least through mid-century, what the Northeast climate, could look like if we remained on a business as usual pathway. And so the way we do that is we take projections from global models and we can downscale them to regions like the Northeast US, and then we can further downscale them to points if we want. So we can take it and actually look at data for an individual watershed. And so we can do it for the Mantango Creek watershed, for example. And these models come from climate scientists. We got our models from Catherine Hayhoe from Texas Tech University. She gave us 9 models that represent a whole suite of possible futures from warm and wet to warm and dry. All the models have different sensitivities. I picked one to highlight that just kind of represents a middle of the road kind of scenario. So it's not, overly hot, not overly cool. It's kind of the mean, relative to the 9 models that she had access to. And so that model is the Hadley model, and it's actually out of the UK. So basically what I've done is plot here, temperatures, the average temperatures that we currently have, and then I'll show you what some of the projections look like. So this is going to be a little bit Pennsylvania-centric because I've given this talk quite a bit for folks in Pennsylvania, but you can see from the maps, of the rest of the Mid-Atlantic region and Northeast U.S. what, some of the projections look like. So for Pennsylvania, our average temperature is 51 Fahrenheit or 10.5 degrees C. As we move out into the mid-century, which would be 2015 to 2044, we're looking at an increase, to 52, degrees Fahrenheit, 11 degrees C. And if you consider the long term, you look at like over the long term how that how that reflects the warming relative to the long-term mean. We're looking at increases in 3.5 to say maybe 2 degrees C relative to the long-term mean in Pennsylvania. But everybody warms up through mid-century. It gets warmer, and so there's no doubt about that. All the climate models show this. There's none that show any cooling for Pennsylvania or for anywhere in the Northeast. You can look at extremes in temperature, which are always kind of interesting to look at. You can pull out, for example, the highest maximum temperature in any given year, and you can take a look at how might that change for say our watershed, the Mantango Creek watershed. And that's what I've done here. So in 1975, the highest daily maximum might have been 95 degrees Fahrenheit plus or minus 2 degrees Fahrenheit. We get out to 2025, you're looking at a highest daily maximum temperature of 98 plus or minus 7 degrees Fahrenheit. And if you get way out into the century where things become a little less certain, but it's just worth pointing out that some of the climate models show upwards of 118, so it's 108 plus or minus 10 degrees Fahrenheit, the highest daily max temperature in a given year. And if you get all the way out to 2100, they're showing perhaps over 120 for the highest daily maximum temperature you could see in a given year. Now, you have to take this, with a grain of, because these are assuming no changes in emissions, and there's still some uncertainty, in these models. But warming is no doubt, and the extremes in heat are no doubt to increase. And so these are just possibilities. Growing seasons, for instance, they are, in Pennsylvania, we have a growing season of about 180 days, and these are inferred with temperature data. As temperatures warm, we're likely to see growing seasons shift. We're likely to see warmer growing seasons out to 195 days on average. But you could see here, for parts of the Delmarva, and the eastern shore, out to 270 is not out of the realm of possibility. So you're getting, out to, much into almost a full year's worth of growing season length. And you can see that also here for the Mantango Creek watershed, which is the watershed where we work. When we pull out the downscale data and we calculate growing season with temperatures, as you get out towards the end of the century, it's not impossible that you could have a growing season that goes almost year round. That's out to 2100. That doesn't mean that you can also have a growing season that's only about 200, some days. So, even though there's an increase, there's still, this is the range, this line is the mean. So an increase is likely. Frost days are obviously likely to go down because it's warming, so fewer days with frost, which is actually probably a good thing, if you're trying to, if you're worried about trying to combat frost events and you're worried about these early fall springs and things like that, they're likely to be less frequent. In terms of rainfall, like I said before, it's going up. We're seeing it go up already. It's going to continue to go up as we put more moisture in the atmosphere as the planet warms. So 41 inches a year in Pennsylvania is kind of the average statewide, to 44 inches by kind of the mid-century, 2015 to 2044. So more annual rainfall, more rain in any given year than what you had in the past, which translates to about a 10 to 15% increase. Now, and a lot of that's going to come in kind of more extreme events too. So you're going to get more days, say, with an inch of rain in a day. So 5 more of those days are more likely by the end of the century. So more of these extreme rainfalls, less of the kind of the lighter or the moderate rainfalls. So they're going to be going down as you're going to get more rainfall from these extreme events. Especially the ones like these 5 inch per day kind of events, they're also likely to go up. So kind of the point here is that you may get more total rainfall in the year than you had in the past, and a lot of it's going to come in these extreme events, but kind of paradoxically, the future is also likely to be drier, and that's kind of a hard thing to try to explain to people. But it's interesting that a lot of the models actually show drying, and what they're showing is that there's going to be these longer periods of dry days. So this is the change in maximum consecutive dry days. And there's a likelihood that you're going to get these expansive dry periods where you don't get rain. And then when it does come, it's going to be more extreme. So you'll get more rain in a short period of time and then longer periods of dry spells. And so at the end of the year, when you add it all up, you may have more rain than what you got in the past. But if it's coming in these big events, you're not getting the even distribution of rainfall that you used to get. And so 80% of the models are showing those kinds of possibilities. And recent study that came out in Science just showing the likelihood of drying across the entire North American continent just as the planet warms. There's going to be a lot of demand for evaporation as the temperature warms, and so most areas are likely to dry. And a lot of the drying is going to be likely in the Southwest and in the central part of the United States, but even in the Northeast, you're looking at potential declines in soil moisture. Which will be, proposed challenges, especially if you have these longer dry stretches and you're getting more extreme rainfalls, on top of that. So to summarize for Pennsylvania, this just takes an animation from the Union of Concerned Scientists, and it just shows how Pennsylvania's climate is likely to move. If you want to get a kind of a mental image of what the climate might look like if you stayed on a business as usual pathway and we didn't make any changes with emissions, this is the likely shift in climate that you could see. And so we'll start with eastern Pennsylvania. So this shows where, the 1980, the normal climate, the baseline climate. So eastern Pennsylvania becomes a little bit more like central Maryland as you shift from 2010 to 2039. If you move further out in time, it has a climate a little bit more like southern Virginia, and by the end of the century, eastern Pennsylvania's climate is likely to be a lot more like southeastern Georgia. For western Pennsylvania, you've got a climate of western Maryland in the next, next 2 decades. By mid-century, you're shifting to central Kentucky, and by the end of the century, more like northern Alabama. So with that, what are the resources that are out there, that you can turn to, if you're interested in, understanding more about some of the projections and how, you might be able to adjust to some of the changes that are, that are coming. So the USDA has a network of these climate hubs, that are going all across the country. And there's one in the Northeast. There's 7 in total. And the whole point of the climate hubs is to help farmers and foresters not only adapt, to climate change, but also to mitigate climate change. And they're putting up all kinds of resources. They're working with all the land grant institutions, the major universities in all across the Northeast and all across the country, working with extension and trying to put out resources to help, farmers, understand some of the projected changes and options that, that they may, adopt, to adjust to those changes. And so here's the Northeast hub. And one of the things that just came out, this thing was just Dan Dosty out of the NRCS office in Harrisburg is working on behalf of the climate hubs. And they've put together a report. It's at Adaptation Resources for Agriculture. This is currently available online. And so you're able to go into the book. And it's supposed to be very specific to your situation. So if you're dealing with extreme rainfall events, or you're trying to figure out how to prevent erosion with cover crops or other kinds of things, there are things that are tailored specific to your farm. It's kind of help you work through a decision framework to come and make decisions about how to adapt, to climate change. This is the website link for it. So it's available as a PDF right now, and there should be a hard copy available in the near future of this book. If you're interested in just projections or data, there's lots of resources out there, for different kinds of data. My favorite over the short term is really just going to the Climate Prediction Center website. It's NOAA's National Weather Service Climate Prediction Center, and so you can use it just to look at temperature projections, for example. If you want to know, 1 month from now, is it going to be warmer than normal or cooler than normal? What's the likelihood of below normal rainfall or above normal rainfall? You can look out 1 month, 3 months, a year, and you can look at how, what the projections are looking like. You can say, oh, wow, there might be a drought, there's a high confidence of a drought in, several, months from now, or drought's likely to get better, or it's likely to get worse. You can look at those kind of projections on their website. It's really helpful. I use it all the time just because I do a lot of research in hydrology. I want to know, am I looking at above normal rainfall? Do I need to go out and sample in the next couple months, or is it going to be dry? Can I shut it down and just go type a paper or something? And another thing that I think is really helpful is Cornell has a climate smart farming website and there's all kinds of decision support tools on their website that relate to climate. And so they have, for example, an irrigation scheduler, which is tied to your farm. Or it's location specific. You can put in the location of your farm, and it does water balance calculations, and it can tell you, how much you need to add for irrigation over certain time frames. They have a frost and freeze tool, which is really, really great, and other such tools. And so I encourage you to check that out because the tools they have on there are really, really useful, and they're all for the Northeast U.S. And if you really want to look at the long term, if you're interested in the long term, then there's the U.S. Climate Resilience Toolkit, which I think is great because you can put in your zip code, and for any zip code you can look at past data all the way back to 1800, look at trends, it graphs things out for you, and then in addition to that, you can also go out to 2100. So if you want to look at the past, you want to look at the future, you can engage with all of the climate model projections and possibilities for different kind of emission scenarios through this website. It's really great, and it just came out just not too many months ago, so I encourage you to check it out. And so with that, I really appreciate your attention. Thanks a lot. I just wanted to acknowledge folks from USDA who helped largely with the trend analyses for the watersheds, Mantango Creek, Ann Stoner and Catherine Hayhoe. They're climate scientists out of Texas Tech, supplied all the regional climate models that we used with the projections. And then Haiming Liu was a visiting scientist with us in our lab for a couple years and assisted with the long-term trend analyses. So thanks a lot for your attention, and I'd be happy to take any questions now, or if you want to catch me later, that's fine too.